My name is James Thompson. I'm a NIST physicist here at GILA in the University of Colorado. And this is my cold atom lab where we actually laser cool and trap atoms, and we do interesting things in the quantum world.
And then the actual superradiant laser photons are coming out.
So we've developed something called a superradiant laser that operates in this really strange regime that's interesting from a physics perspective, which is that it operates with very few photons around to drive the stimulation process that you'd normally associate with lasers. But in addition, it's very interesting from a technology perspective because we show that the color of the light that's emitted by this laser is very insensitive to the environmental shaking of the things you put around the laser. And that actually turns out to be one of the chief problems for making the best lasers we can here at NIST and a few other places in the world. So in our laser, we actually trap about 1 million atoms of rubidium in between two mirrors, and we levitate them there. And then those atoms, while they're sitting between the mirrors, they spontaneously synchronize with each other. This is kind of like crickets that all could chirp independently, but after a while they hear each other and they start chirping together. And so these atoms synchronize and they start actually emitting light together. And they emit it what we call in phase, and that's like the crickets chirping together. And so they begin to emit in phase with each other, and that leads to a huge enhancement in the amount of light we get out. We call that enhancement stimulation. In a normal laser, essentially you build up many, many quanta of light called photons bouncing in between the mirrors. And they're the things that actually carry the information that actually make this laser tick like a clock in a very regular fashion. Okay? And in fact, in a normal laser, you have millions and millions and millions of these quanta of light bouncing around. In our laser, we actually are able to operate and see that it behaves just like a laser, but with less than one photon in the cavity. In fact, we can operate with as few as 1/5 of a photon on average inside the cavity. And that means sometimes, if you were to look between those mirrors, you would even find that there's no light inside the cavity. There are no photons. And so that's a really strange regime for a laser to operate in. It's very novel. And we think in and of itself, that's really interesting and neat to do. And we want really precise colors. Why? Why do you want precise colors? Well, because you can think of light as like a pendulum. It's a ticking object. And we actually use it to make very, very precise atomic clocks at NIST and here at GILA. In addition, you can also think of it spatially, that when you take that light and you actually launch it and you allow it to propagate in space, it becomes a kind of ruler and it allows you to measure distances very precisely. So using some of the concepts we've demonstrated in our setup, in the future you might be able to make much, much more single color lasers and be able to use those to make very, very much more precise measurements and better atomic clocks for things like global positioning systems that we use in our cars every day,